Okay, Noam, you're good to go?
Okay, thanks, Laurent.
Yeah, I was just asking you if you're ready. I have to.
Oh, yeah.
I have to properly introduce you before that.
Okay.
Yeah. Okay.
That was an introduction.
Okay. So yeah, good morning, everybody. Good evening for some of you online. Welcome to the second day of the meeting, and we're going to start today with Noam Greenberg, and he will give us a dynamic classification of Borel Wadge classes. Thank you.
Thanks, Laurent. And I'd like to thank the organizers for inviting me to give a talk and apologize that I can't make it in person this time, but hopefully soon. This is joint work with Matthew Harrison-Trainor and Dan Turetsky about Wedge classes. So what are Wedge classes? So to keep things simple, we will work solely in bare space, space of all functions from natural numbers to natural numbers. And given its topology, we define a Wedge class to be a collection of subsets closed under taking continuous inverse images, pre-images. And the Wedge class is principal if it is generated by a single set. It's a collection of all continuous pre-images of a particular set. Notation that I won't be using too much, but here it is that A is Wedge reducible to B if A is a continuous pre-image of B. So you can think about it as a continuous version of many-one reducibility, except that instead of sets of natural numbers, we're using sets of real numbers, if you'd like to call elements of bare space reals. And the problem on the hand is to describe all Wedge classes of Borel sets. So to begin with here, so just some particular simple examples of Wedge classes. What are Wedge classes? So the familiar classes are the sigma 0 alpha classes for countable ordinals alpha, the collection of complements pi 0 alpha, the intersection of sigma 0 alpha and pi 0 alpha, which are the delta 0 alpha classes. And then also the Hausdorff difference hierarchy, starting with sigma 0 alpha classes. So here's a definition of what that means. I take a non-zero ordinal eta, and I take an increasing chain of length eta of sets in the class in parentheses sigma 0 alpha. And then for every real, to decide whether it's in or out, I look at the least ordinal zeta such that x is in A zeta, and ask about whether the parity of zeta is the same as parity of eta or not. And according to this answer, I say yes or no. What do the Wedge classes or Wedge degrees look like? The fundamental theorem of Wedge is also sometimes known as the semi-linear ordering principle, or the Wedge comparability lemma, is that for two Borel sets A and B, either A is Wedge reducible to B, either A is a continuous preimage of B, or B is a continuous preimage of A complement. That C is for complement, the bare space minus A. So that means that they're kind of almost linearly ordered. There will be many cases where a set and its complement are not comparable, but if I kind of like ignore the difference between them, then what I have is a linear ordering. And then Martin and Wedge proved that in fact it is well-founded. So if after I merge a class and a set and its complement, these classes are well ordered. Of a fairly long order type, and there's a deep analysis of the order type of all Borel Wedge classes. The order type, if you go for all Borel, is corresponds to base omega 1 Veblen functions. But I mean, we can see how it goes for the very first levels. For delta 2, there's omega 1 many classes, basically following the Hausdorff difference hierarchy. For delta 3, each level of the Hausdorff difference hierarchy is split into omega 1 many classes. So and you repeat that. So the ordinal corresponding is the omega 1 power of omega 1 and so on. And this is just the delta 0 ends. And once we get to delta 0 omega, this class is much bigger than even the union of the delta 0 ends. So there's lots and lots of classes. Here's a picture. So first of all, just a little bit of notation. The check, gamma check, is called the dual class. It's the collection of complements of sets in gamma. And delta of gamma is known as the ambiguous class of gamma. It's the collection of sets that are both they and their complements are in gamma. And we say that a class is self-dual if gamma equals its dual. Here's a picture of the very lower levels of the hierarchy of Wedge classes. All these dots correspond to principal Wedge classes. And we start at the bottom with just the empty set and just all of bare space. The next level here is the Clopen sets, the open sets. These should be boldface. I just didn't bother to boldface them here. Open sets, closed sets. Then for the next non-self-dual pair, I've got the D, differences of open sets, differences of closed sets, and the intersection of the classes. And so on. These lines mean containment, and the general pattern should remind you of the arithmetical hierarchy. But as I said, it's because it's so long, we also have to discuss what happens at limit steps. So at limit steps, there's one of two patterns, depending on the cofinality of all the order type of all the classes that came before. So if you've got a limit point of cofinality omega, then there is a specific class there that is at least upper bound of that sequence of cofinality omega. But if the cofinality is omega 1, then there's no least upper bound. Okay, so what does it mean to describe all Borel Wadge classes? And there's been a number of solutions over the years, and solutions that were also informed by generalizations. So for example, Duparc described Borel Wadge classes not only for bare space, but also for spaces of the form kappa to the omega, where kappa is an uncountable cardinal. So there it's kind of like the same picture of an infinitely branching tree, except that instead of in bare space, there's an omega branching. We're now looking at kappa branching trees and sets of paths. Selivanov generalized the analysis for sets to analysis of K partitions. As we shall see, we can of course identify, as we do always in computability, we identify a set and its characteristic function, and so we can just look at functions that have other values other than just 0, 1, and Selivanov did this for K-valued functions. And then Takayuki Kihara and Antonio Montalban generalized this to all functions into countable beta quasi orderings, and they give a really nice analysis of what do these classes look like. But I want to go back to essentially the original solution, which it is presented in a 1983 paper by Louveau. He credits a lot of the work back to Wedge, and Wedge's work for a long time was only available in his thesis that was published again a long time after he finished the work. So I will refer this to as Louveau's solution because his paper is the first complete treatment. And he basically gave an inductive definition. He basically said, let's start with a bunch of classes, and then I will tell you how to generate more classes from them. And the classes that he starts from are just the class, which is the empty set. The class is d eta sigma alpha. So those are those classes in the Hausdorff difference hierarchy. Excuse me. And then from these building blocks, how do we generate more classes? And it gave the following operation. So the first operation is called the one-sided separated union. which are again classes of this form. I break up my space into a set C and its complement, where C is one of those d eta sigma alpha sets. And on C and on its complement, I apply two, I take a gamma set and a gamma complement set and restrict to them. So that's what one-sided separated unions are. And then the similar operations, they just get more complicated. So what two-sided separated unions are instead of two sets, set and its complement, I have two disjoint sets in d eta sigma alpha, and I'm telling you what happened on each one of those two sets and what happens on their complement, on the complement of their union. So it allows me to mix more classes, and then I can mix infinitely many classes by taking what are known as separated unions, where I have infinitely many disjoint d eta sigma alpha sets, and on each one I apply, I intersect it with a set in a class gamma n. And the most complicated operation appearing in Louveau's paper is this notion of separated differences, which kind of like takes on separated unions and builds even more. And I want to give you the slide basically to tell you what the original solution was, because we kind of like developing on it. But you don't need to remember the details of all exact definition of what a separated union is or what a separated difference is. I want to give you the flavor of what these definitions look like. So why look at Louveau's solution, which, while comprehensive, it's not the simplest one. Well, we had an ulterior motive. The ulterior motive was we were trying to understand what's the reverse mathematical strength of Wedge's comparability lemma, that lemma that said for all A and B, either A is reducible to B or B is reducible to the complement of A. And we wanted to show that essentially provable in the weakest possible system of arithmetic transfinite recursion. And the story there is that in really fundamental work in the later 80s, Louveau and Saint-Raymond showed that this comparability lemma is provable in second-order arithmetic. And this was very surprising because all results that came before for classes larger than Borel indicated that Wedge's lemma is really strong. Why is it strong? It's because it's equivalent to determinacy. So for example, Harrington showed that pi11, comparability for pi11 sets is equivalent to pi11 determinacy, which is not even provable in ZFC. It has large cardinal strength. And then Hjorth generalized that to pi12, and the natural way to deduce Wedge's lemma is to deduce it from determinacy. It's an immediate consequence of the determinacy of the Wedge game. So it seems like the original way that Wedge proved his lemma was to invoke Borel determinacy, proved by Martin. Now, as we know, Harvey Friedman showed that Borel determinacy is really strong. It is ZFC provable, but it requires uncountably many iterations of the power set. So it's definitely well beyond second-order arithmetic. So the work of Louveau and Saint-Raymond showing that Borel-Wedge comparability is provable in second-order arithmetic was really striking. It really separated it from determinacy in the Borel setting. So there's something special going on in Borel, and we wanted to understand really just how it works. And so why we want to go back to Louveau's solution is that something like that is actually required in any kind of proof of Borel-Wedge comparability that avoids determinacy. And one of the key steps is to show that every Borel-Wedge class has one of the descriptions that is given by the list that I gave so far. That there will be caveats later with respect to non-self-dual classes, but we'll get to that. So how do you prove that every class is described? Chiara and Montalban gave really nice descriptions of Borel Wadge classes in this very general setting. How do they prove that every class has its has a name, so to speak, has a description? They use kind of grand induction. They use induction on the Wadge ordering, which is great, but I mean, we saw just how long this ordering is, and you can see that this is very set theoretical. It seems to be completely undoable within the confines of second-order arithmetic. So we need a different approach. What Louveau did, instead of doing an induction on the Borel on the Wadge ordering, he basically kind of like took the collection of all of the classes that he described and then said, well, let's look at the ambiguous classes of described classes, the deltas. Let's try to understand them. And then basically we will have some kind of argument that says that there cannot be any holes. We will argue directly that there's no room for any other Wadge classes other than the described ones. Louveau's classification, so it's fairly complicated. The proof of the classification works is fairly complicated, and so the first step is we wanted to use it, so we wanted to understand it, and then it became we felt like to understand it better, maybe we can we streamline, can we light out can we actually kind of spell out what makes it work. And we're interested in it from the point of view of computability theory. So we want to really understand all of these set theoretic arguments through dynamic lenses. So what do I mean by that? So here's an example. Top proposition is a kind of like generalized boldface version of Schoenfield's limit lemma for type 2 spaces and for real sets of reals rather than sets of numbers. A function from bare space to the natural numbers is boldface, delta 02 measurable. In other words, the inverse image of every point is sigma 02, equivalently delta 02, if and only if it is approximable, if and only if the value of the function on each real x is determined by an approximation procedure that changes its minds finitely many times. And so we've got this function from finite strings to natural numbers that guess, f of sigma says, my guess is that capital F of x is this number for all x extending me. And it will be right on some x's, and we might be wrong on some other x's. But for every particular x, as we go along, this approximation stabilizes. It's a kind of continuously approximable, if you like. And this can be deduced by looking at the light-face version, the effective version. So light-face delta 02 measurable is the same thing as having a computable approximation, just like in the limit lemma by Schoenfield. How does this generalize to higher levels of the Borel hierarchy? There's a very similar picture. A function is delta 0 on a 1 plus alpha plus 1 measurable. Forget the first 1 plus, say alpha plus 1 measurable, if and only if it has a computable, not an approximation, but an alpha approximation. What is that? It's again, I'm going to have a decision procedure or guessing procedure. Every string, finite string, is going to have a guess, little f, lowercase f of sigma. What are the values of uppercase f of x for the infinite sequences x extending sigma? And instead of stabilizing on all of the initial segments of x, I just look at those initial segments of x that, well, technically speaking, are alpha true stages for x, or alpha true initial segments for x. Now, this is Antonio's true stage machinery relativized to oracles, and I gave a couple of other talks about the true stage machinery and descriptive set theory, and this is part of the work that I want to kind of brush under the rug. This is not the focus of today's talk. Today's talk is kind of complementary to those other talks that I gave. So I don't want to define true stages. For those of you who know, these are the kind of like finite approximations of the iteration of the Turing jump alpha many times. Because to be delta's alpha plus 1 measurable, that's the same thing as being computable after taking alpha plus 1 many jumps. And so what this says is that to be delta alpha plus 1 measurable, it's the same thing as first taking alpha jumps and then doing a kind of on top of that a delta 2 approximation. So roughly this is what this proposition says, and I don't want to talk too much about that. But what I want you to take away from that is that even when I go to higher ordinals that requires taking lots of Turing jumps, there is this kind of approximation procedure. That the process of approximating is more complicated in the sense of telling what the limit is, but it's still the situation that every finite initial segment has an opinion, and it's, in some sense those opinions coalesce to the correct value along every real. This proposition, unlike the previous one with the boldface delta 0 to immeasurable, is inherently effective. Like, I cannot state this in boldface because the alpha true stages are essentially effective notion that that change as I change the oracle. Right, so if I want to state it in boldface, all I can do is to say for every oracle Z, the following effective relative to Z thing happens. Okay, and that was characterization of delta alpha plus 1. This pesky 1 plus alpha, which is you know, I just couldn't bring myself to just erase it. It's just this adjustment that I have to do for the finite levels, because in this setting, open really should be sigma 0, 0 rather than sigma 0, 1. But other than that, if you see 1 plus alpha, just say alpha. So I can also understand the Hausdorff difference hierarchy in these dynamic terms. What does it mean to be a set which is d eta sigma 0, 1 plus alpha? Remember that the static description of that was that I had this eta sequence, increasing eta sequence of sigma 0 alpha sets, and for each real I was looking at the least zeta, such that x was an a zeta, and I was looking at the parity of that. That was the static description. Here I'm doing this, and here I'm doing this light phase, so that just basically the same definition, except that all of this the sequence are uniform, the effectively sigma 0, 1 plus alpha. So what this class is a refinement of the lemma. Each one of those sets is delta 0 alpha plus 1. So it has this computable alpha approximation. What makes it at that particular level of the Hausdorff hierarchy is that along with this approximation comes an ordinal witness function, an ordinal valued function that tells me essentially how much space do I have left to change my mind about the value of the function I'm approximating. And the particular properties of this ordinal witness function is if now this subscript alpha means an alpha true initial segment of sigma is an alpha true initial segment of tau, so that's the thinning of the initial segment relation to things that agree about the alpha jump. So if tau extends sigma for the purposes of an alpha approximation, then the ordinal cannot go up. And if tau extends sigma for the purposes of alpha approximation, and tau's guess about the value of the function being approximated is different from sigma's version, f of tau is not f of sigma, then the ordinal has to go strictly down. And so basically what this means is that this function beta is a witness to the fact that this approximation actually converges on stabilizes along the alpha true initial segments of every real. So it actually approximates a well-defined function. And then the last condition, what makes it particularly eta, right? So that sorry, this is a typo here. The values of beta are in ordinals eta. Oh, that's terrible. Beta is a function from strings to eta. So if eta is omega, then what's written is correct, but I'm allowing ordinals below and above eta. So what this says, the third condition says, is that if the value is eta, if the value is the largest that is possible, then then the answer has to be no, has to be out. I'm trying to compute a characteristic function. That means that I'm starting my approximation with out, and then if the ordinal decreases below beta, then I can change my mind as I go. And so this essentially gives a effective version of the Hausdorff-Kołakowski theorem. The Hausdorff-Kołakowski theorem gives an analysis of the classes delta 0 xi plus 1 boldface, in terms saying that each boldface delta 0 xi plus 1 set is d eta sigma 0 xi for some countable eta, and that the effective version of that is true, with eta being a computable ordinal. I have to be careful here because unlike sigma 0, light phase sigma 0 xi, the d eta classes are not extension, I'm not sure what the word is, they depend on the presentation of eta. But essentially, after we've translated all of these notions to effective approximation notions, what this theorem, or the way to prove this theorem, is to say every converging approximation has a computable ordinal witness function for the approximation, for the convergence of this approximation. And that is true. So if you like, this really generalizes, resembles the Ershov hierarchy for sets of numbers, but there's topological restrictions here. Okay, so let me get to our solution. What are the described classes? In some sense, it's not really a new solution. The descriptions as kind of appear in a paper of Louveau and Saint-Raymond in 1987, but we kind of present them and think about them in ways that I think are quite different, and I'll talk about that. So here I want to be precise and try to not lie at all. So here's a definition. What is a description of a Borel Wadge class? It is a labeled well-founded tree with the following properties. The label of a leaf is either 0 or 1. The label of a non-leaf is a pair of ordinals, xi and eta. As I go up the tree, the xi ordinals are not allowed to go down. They're only allowed to go up. And if rho is not a leaf, then at least we have some specialized child, which we guarantee is on the tree. And to top it off, there's an oracle y gamma accompanying the class that computes all of this information. I'm really not going to talk too much about this business of the oracles. I wanted to put it there so that it's the definition is close to the truth. The thing to note is that if I take any node on one of these labeled trees and just kind of like make it the root and throw away everything else, that itself is a class description, a simpler one, if you like. Okay, so that's a description of a class. What's a description of a set in the class? We call that a gamma name for a set in gamma. What it does is it takes the gamma tree, and on each non-leaf node, it gives me a approximation procedure for a choice of a child. Right. So formally speaking, this is a pair of functions resembling our characterization of d eta sigma 0 alpha sets. it is the function f that at that node rho, for every initial segment of a real, chooses a child of rho on the tree. That choice is accompanied by an ordinal that tells me how much space do I have to change my mind later. If tau extends sigma for the purposes of this Z computable approximation, which involves implicitly taking psi many Turing jumps, the ordinals cannot go up. If the same situation holds and I've changed my mind, then the ordinal has to go down, so that eventually those mind changes will stop along every path. And if I, at the very beginning of the process, if I'm starting at the top ordinal, I have to choose this default outcome. So 0 is the default outcome. It's the one that I have to choose first and then maybe change my mind about. So that's a name of a set. What is the set that is being named? So let n be a gamma name and let x be a real. And what we're going to do is, for that real, we're going to choose a path on the labeled tree gamma. We start at the root. If we've reached a non-leaf row, then we want to choose one of the children. Well, we take that function that approximates the choices and we take the limit along the z psi true initial segments of the real. We perform this approximation and we take the limit. And we keep going, and because the tree is well founded, we'll get to a leaf. That leaf is labeled either 0 or 1. That information is supplied by gamma, not by n. And the function computed by that name on that input, the real x, is that 0, 1, the label of gamma. So that's the function, and identify the function with it's a 0, 1 valued function, so it's the same thing as a set. So I can think of gamma z, the light face gamma class with oracle z is the collection of all all sets with z computable names. This condition z computes the class description gamma so that anything would make sense to the oracle z. And then the boldface classes do this for all oracles. So here are some examples, a couple of pictures. What are those class descriptions and what are the classes that they describe? So the simplest tree is a tree that just has a root. And so that root is a leaf, so it has a label 0 or 1. And so our definition means that to determine a name basically does nothing, because a name only gives information for non-leaves. So for every x, this approximation or guessing process ends immediately with this is the leaf and the value of the function is 0. So basically it only computes the constant function 0. So that's the obviously the indicator function of the empty set. If I change 0 to 1, then I get the indicator function of everything, of all of their space. Now let's have a root and 2 leaves. The left one labeled 0, the rightmost one labeled 1. And in those pictures, the left one is the default one, the one that I have to take first. If psi equals 0, then I'm not taking any jumps, so I'm doing a normal approximation in the sense of Schoenfeld. And if eta equals 1, that means I'm allowed to change my mind at most once. So this means that for any given real x, I'm starting by being forced to take the outcome that says out or 0, and then possibly I will change my mind and go to 1. Right? That's the same thing as open. This is, you should think of this as CE in some sense. Something happens and you change your mind from no to yes. And once that happened, you can't change your mind back. If I flip the labels, then I get co-CE or closed. Same picture, but now I can just generalize the pair of ordinals to be psi, and instead of remove this equals 1. So any eta here would give you the class d eta sigma 0, 1 plus psi. And the reasoning is exactly the same for open and closed, except that if eta is bigger, then I'm allowed to change my mind more times. And that corresponds to levels of the Hausdorff difference hierarchy. And if xi is bigger than 0, that means that I have to take some xi many jumps, which allows me to go into to replace open by sigma 0, 1 plus xi. So those are the Louveau's basic classes. Now, how do I represent classes that are compound classes, classes generated from other classes? So here's, for example, the tree for separated union. If I already have gamma and I already have its dual, then I put gamma dual as the default and gamma as the one that I'm allowed to move for. And this is the tree for separated unions. This is the tree for two-sided separated unions. I'm starting with a lambda computation procedure, and then I can switch back and forth between gamma and gamma dual. And the separated union is I'm starting with gamma 0, and then I can change my mind back and forth about which of these infinitely many outcomes to take. So all of Louveau's classes have a nice pictorial representation. So a couple of basic facts. Each called boldface gamma a described class, a class that has a description. First of all, to say it is a Wedge class, it is closed under taking continuous pre-images. And it has a universal set. And if you can prove the set theoretically, but if you're working from the point of view of computability, the reason that it has a universal set is that I can list all, effectively list uniformly in an oracle all possible names in that class. And how do I list names? Well, that means for each node, I need to list essentially eta CE functions, starting with the default value. And this is where the default value really matters. I wouldn't be able to do that if I didn't have this default value, right? Because if I'm trying to list eta CE functions, I need to take into consideration the possibly partial approximations that I have. And while I'm waiting for the approximation to start, I say default value. That's what makes the effective listing possible. And that's the reason that those classes have universal sets. And the consequence for that is that those classes are principal and non-self-dual. The main theorem is that every non-self-dual Borel Wadge class is described. And I've been mentioning these things as I went, but I wanted to reiterate is that while these descriptions in some sense appear in work by Louveau and Saint-Raymond, we think about them differently. And we think about them as being dynamic procedures of decision rather than describing sets given by Boolean operations, the sets of the form, the intersection of that with the union of that, and so on. The object that we're describing, the sets, are not actually really sets, they're functions, right? If I change the labels of the leaves, then I can do any kinds of other functions. So you could use these descriptions to describe more generalized situations. But for our purposes, even if we're just looking at 0, 1 valued functions, what this allows you to do is to classify partial functions. And it turns out that from our point of view, that's the right way to think about it, is that for the purposes of classifying total functions, you need to consider partial functions as well. I will be running out of time, so I'm trying to think about a good time, good place to stop. It will be getting slightly more technical from now. So let me give you just basically one of the basic definitions that we have. So first of all, we have this notation of a subset for class descriptions rather than classes, by which we mean effective containment. Lambda is a subclass of gamma effectively if I can take any lambda name and transform it computably into a gamma name of the same set. And this y lambda computes y gamma is necessary for this process to make any sense. Lambda is strictly below gamma means lambda is below the delta of gamma. Lambda is a subset of delta of gamma. A sequence, an infinite sequence of classes is monotone. It should be monotone alternating, but we don't have monotone. This is the only kind of monotone we're using, so we kept it short. Monotone if gamma n is contained in the dual of gamma n plus 1. And a class description is monotone if for every non-leaf, remember, if I look at a child and I look at all of its children, a node, all of its children, each one of them is a class, right? I can think of the well-founded tree as giving the description of how to build the class from simpler classes, starting at the leaves and then going down the tree. So those immediate subclasses, the children, that has to be a monotone sequence and above every non-leaf row. And the two main kind of subcases, which by going to subsequences are really the only two cases, is this case where it stabilizes into a class in its dual, or it's strictly increasing all the way to the end. And essentially the difference between these two cases in some sense is the reason that Louveau had to have so many classes, because he treats them separately, but you don't actually need to. So an acceptable description is a description that satisfies one of those two definitions of theorems, right? So every non-subdual Borel Wadge class has a description that is monotone, so that this has this really regular shape at every non-leaf. And I can also either require that every eta ordinal is 1. So instead of eta many mind changes in each approximation, I just change my mind once from default to possibly non-default. Or I can require that the psi ordinal, the one that tells me how many Turing jumps I need to take, strictly increases for non-default outcomes. And here's, for example, some information that you can glean out of looking at those descriptions. Van Weesep, I think it's Van Weesep, proved that if you have a Borel non-self-dual Wadge class, then exactly one of the classes has the separation property. The separation property is the two disjoint elements of the class can be separated by something in the delta of that class. You can think about them as one has a kind of sigma type behavior, one of them has a gamma type behavior, kind of like CE and co-CE. And we can tell if you've got an acceptable class description, then we can look at the tree and tell you which one it is by simply following the leftmost path and getting to the leftmost leaf and tricking its label. So that basically tells if the overall default outcome is in, you have the separation property. If the overall default outcome is out, you don't. And then there's the reduction property. This is the same property that CE sets have, right? If you've got two CE sets, then you can go to produce CE subsets where the union is the same thing, but they're disjoint. You can basically choose you went in first there. So not all pairs of classes have the reduction property, and it turns out that we can look at the class descriptions and say that it has a separation property if hereditarily it doesn't, no, it has the reduction property if it hereditarily doesn't have the separation property. Every default leaf is labeled 0. Okay, I've got 5 minutes. I don't have time to go through all of the remaining slides, but let me just give you just a taste of what it looks like from this point. So recall that this 1, 2, 3 are the various possibilities for delta classes, according to those pictures of hierarchy that I put in the beginning of the talk. I have a gamma and a gamma dual, and below them, or to the left of them, lies the ambiguous class, gamma intersect gamma dual, delta of gamma. Either it's a principal class and it is the successor of a different non-self-dual pair, or it is principal and it has cofinality omega, or it is non-principal, it's just the union of all the classes but strictly below gamma, and then it has that list of classes as cofinality omega 1. How can I tell which case it is? Look at the class description. Delta of gamma principal if and only if all psi ordinals along the leftmost path is finite. It ends at a leaf, the leftmost leaf. I look at the psi ordinals and see if they're all 0, then this is principal. If one of them is non-zero, then it's not. Now, one thing I'd say to take away from this is that this is kind of like classification of these gammas into 3 cases, but in some sense, the Turing jump is kind of masking something more fundamental that's going on here. Really, there are 3 types, but they're not quite those 3 types. There's what we call countable type and uncountable type, and then there's the special class of type 0 for the very basic classes, the nothing and everything. Uncountable type means every function in delta gamma belongs to some describable class below you. Countable type means every function in delta gamma, the domain can be broken up into countably many sets in a fixed, such that on those sets, you're in a lower complexity in a fixed list of classes. So that kind of like the delta of gamma is really kind of the union of those theta ends. And the main theorem for this talk is that each acceptable description has one of those 3 types. And if it has, this is just a restatement of what it means to have countable type. If you have countable type and the ordinal at the root, the psi ordinal at the root is 0, at the root you don't take any Turing jump, then you look at this sequence that witnesses that the sequence is the fact that gamma has countable type. And remember those 2 cases for monotone sequences. Either it stabilizes on a non-self-dual pair, theta and check theta, theta dual, or it doesn't. And this covers both the cofinality 1 and the cofinality omega cases. Both of them have countable type, and whether it's cofinality 1 or cofinality omega just depends on this pattern of the sequence of thetas. If it's strictly increasing, then that is a cofinal sequence that for which delta of gamma is the least upper bound. If it's just kind of eventually theta dual, then that's the predecessors of delta of gamma. I think I should probably stop here. So I would say thank you. I hope this wasn't too confusing. We're in the process of writing the paper, so these things are kind of coalescing in my mind as time goes by. So I think there's a nice picture emerging here. We're still in the process of figuring it out precisely. Thank you.
Do we have any question? Yes.
Hi, I have 2 quick questions. So you just mentioned the bare space. Did you also look at the Cantor space?
No. There's it's slightly more complicated. The difference between Cantor, bare space and other spaces is at the lower levels, right? Once you get to like F sigma G delta sigma 2 something, then all these spaces become isomorphic. So there's not much between them. It's for bare space, the picture is the cleanest. And there's quite a bit of work on all kinds of other spaces, and I'm sure that this can be adapted to those spaces, but there's only so much we can do.
Thanks. And the other question is, did you also look at converse direction? So how to get strength from Wedge determinacy for certain classes?
No, there is work. As a group in Portugal, Spain, Manuel Orrero, I'm sorry, I didn't remember the names of his co-authors. He gave a talk at Logic Colloquium at some point last year, I think, and they have work in that direction. Like so, determinacy for delta 0, 1 and Wedge determinacy for delta 0, 1 implies on bare space implies this, on counter space implies that. So they have partial results in both directions for the lower level Wedge classes up to sigma 2, pi 2, something like that. The reason we looked at ATR naught is at some point, I don't know if this quote is apocryphal. I quote Simpson as saying that ATR naught is the simplest. It should be your base theory if you're doing ordinals and Borel sets. I know that Linda might disagree with me. She has lots of interesting work on Borel sets without ATR naught, below ATR naught. But at first approximation, for things to behave in a minimally reasonable way, you should use ATR naught. And so basically we are working in the analog of RCA naught, so we're not using anything to prove the base theory. But that's just because we are new to this, and we're taking our first steps, and there is other work in this area that's more delicate.
Thank you. Any more questions? Okay, well, I think we're going to thank Noam again.
No, thanks for listening.
And our next speaker will be Neil.